Suppose that at the end of every year, starting at age 28 and continuing through age 70, you invest $3,000 in an individual retirement account with an APR of 4.5% compounded annually. Our job is to compute the value of the account at the end of this period of time, the value of the IRA when you are 70 years old. We are presuming here, as we have in previous examples, that this language means that when you're 70, you're also making one last deposit. As we've understood before, this sum expresses the value of this retirement account at the end of this period, at the end of the year when you're 70. There are many terms, each of which is $3,000 times something, and that something is 1.045 to some power. Right? So where did 3,000 come from? That's the payment amount. Where did 1.045 come from? That's because the APR is 1.045 and interest is compounded once a year. The power, the exponents here, that we have to think about a little bit. The very first $3,000 payment that's made when you're 28 years old sits in the bank from the age of 28 until the age of 70. That means there are 42 full years in which that $3,000 is earning 4.5% interest. So the very first term here in the sum, corresponding to the very first deposit that's made, that has 42 as an exponent. Each successive $3,000 deposit has 1 year less to earn money, so these exponents continue to decline all the way down to 1 here, and finally the last deposit made when you're 70 years old, on the last day of the year, that's the same day that we tally up the whole sum, so it has had no time to earn interest. There are 43 terms in this sum. You can think of it as 1, 2, 3, 4, 5, all the way up to 42 here, counting by the exponents, 1 through 42, and then that leaves one additional term here, the 43rd. We substitute into the formula, 0.045 for I, 43 for N, 3,000 for PMT. We compute that $375,829.21 is the amount of money that will be in the IRA at the end of the year when you turn 70. Our next example illustrates another way of using the formula. Suppose that you'd like to retire with a nest egg worth $1 million. In other words, your goal for accumulated savings is $1 million. You decide to put the money at the end of every year into an account earning 6% annual interest. If you intend to do this 40 times and retire at the end of your 40th year of saving, how much do you need to put into the retirement account each year? Notice that here it is the value of PMT, the payment, that is unknown. We know what the interest rate is. We know the number of payments. It is 40. We're just told this explicitly, that there are 40 payments. And the future value of the annuity equals $1 million. We're told FV and PMT is the unknown that needs to be solved for. So this is simply a job for plugging the known values into their appropriate locations in the future value formula and solving for PMT. To solve, we compute the value of this whole expression, 1.06 to the 40 minus 1, and all that divided by 0.06, that works out to be 154.76197. Then dividing both sides by this 154.76197, we find that the payment equals $6,461.54. What does that mean? It means that this is the amount of money that you would need to put in the bank at the end of each year, so that if you're going to really do that 40 separate times, your accumulated savings will add up to $1 million in the end. Now, you might ask, after all that fuss in previous problems about figuring out the correct number of payments, why isn't there similar fuss here? Because we are told explicitly the number of payments there are going to be. Just to put this computation in the context of evaluating a long sum, as we've done in previous examples, it's always wise to be able to set this up. What do we have? We have $1 million, that's the known future value, equals an unknown payment that we're looking for times 1.06 to the something, plus unknown payment amount times 1.06 to the something a little bit less. There are many of these terms that look like the yearly payment times 1.06 to the appropriate exponent. Now, how many terms are there in this sum? We already know that there are 40 because they told us in the problem statement that there are 40 payments. How do we understand this 39 here? The very first payment that you make is at the end of year 1. You're going to go and tally up the value at the end of year 40. So from the end of year 1 to the end of year 40, 39 years go by. It's worth noting that this very first term in the sum, the result of making that very first payment at the end of year 1, makes a large contribution to the total. Once we've computed how much the payment is, we can see that that very first payment grows into quite a substantial amount of money, over $62,000. That's quite a large chunk of the $1 million total. After all, this is just the contribution of a single payment. We're ready now to make life more realistic by looking at annuities with more frequent compounding. So we can carry out all these same computations when interest is compounded more frequently than once per year, and when payments are made more frequently than once per year. To make these computations simpler, we're going to assume that the frequency of compounding is the same as the frequency of payments. So if interest is compounded monthly, the payments are also made monthly. If interest is compounded quarterly, the payments are made quarterly. But we can put these together and talk about annuities with more frequent compounding. Our first example again involves savings. Suppose that you save $100 at the end of every month, putting it into a bank account which pays 6% annual interest, compounded monthly. Right, so we have monthly payments and monthly compounding. We can ask, what will be the total amount of money in the account at the end of one full year? This is an annuity because we are making many payments, equal payments at regular intervals. So the same $100 is the amount every single month, and there are many such $100 payments. This really is an annuity. Before we start plugging numbers into the formula, let's make sure we understand what this total account value looks like as a sum. At the end of the full year, your account value will be the sum of 12 separate expressions, one for each month, each of which looks like $100 times 1.005 to the something. Where did 1.005 come from? 1.005 is the monthly growth factor. Every month, this bank that compounds quarterly is going to take 6% annual interest and break it into a monthly rate. So think back to what we've done with more frequent compounding. Every month, the bank multiplies whatever's in the account, not by 1.06, but rather by 1.005. Each month, they give you a month's worth of interest. The first $100 that you put in the bank, say at the end of January, sits in the bank for 11 months before you reach the end of December. Thus, the monthly growth factor is applied 11 times to that first $100. It's applied 10 times to the next $100, and so on down the line until that last $100 deposit receives no interest at all. Before going on to the next video, use the future value formula to compute the value of this sum. Find the account value at the end of one full year. Also, carry out the following variation on this problem that'll make you think about some things. In particular, find out how much money there would be in the account at the end of 2.5 years, instead of 1 year, if you deposited $100 at the end of each month, but the annual interest were only 5.4% compounded monthly.